In this lesson, we are finding the probability of independent events and the probability of dependent events. So let's take a look at the definitions. Independent events are events where the occurrence of one has no effect on the occurrence of the other. We simply multiply. So for example, rolling a 6 on a number cube and getting heads on a coin toss. They have no effect on one another, so we simply multiply the two together. In dependent events, events where the occurrence of one event affects the occurrence of the other event, would be the probability of A times the probability of B given that A occurred. Now, this might be dependent on whether you replace or not replace a card. For example, drawing a king from a deck of cards and then drawing an ace. So if I don't put the king back in the deck, I'm now going to be drawing the ace out of 51 cards instead of out of 52 cards. Conditional probability is the probability that B will occur given that A has occurred. For example, a game machine claims that 1 in every 15 people win. What is the probability that you win twice in a row? So the probability that you win is 1 out of 15. With a game such as this is independent because when you start playing the game again, it's fresh. So we multiply the two together. 1 out of 15 times 1 out of 15 is 1 out of 225, which is approximately 0.004, which is approximately 0.4%. Again, these are independent events because you start fresh each time. In the next example, in a survey of 9 out of 11 men and 4 out of 7 women said that they were satisfied with a product. If the next 3 customers are 2 women and 1 man, what is the probability that all of them will be satisfied? Well, let's start with the 2 women. The probability that they're satisfied is 4 out of 7. So the next 2 women coming in would each have their own probability of 4 out of 7 because they can each make up their own mind. They're independent, they make their own choice. Then we have the probability of 1 man being satisfied. That's going to be 9 out of 11. So multiplying all 3 of these together, we get 144 out of 539, which is approximately 0.267. which is approximately equal to 26.7%. Again, these are independent events because each of these men or women make up their own mind whether they are satisfied or not. In the next question, it says if 4 men are the next customers, what is the probability that they will not be satisfied with the product? So what we can do is we can then use the complement. So we're going to subtract the 4 men that are satisfied. So we have 9 out of 11 4 times. We're going to subtract that product from 1, and that's going to give us the customers that are not. So when we take 1 minus multiplying 9 over 11 4 times, we get 6,561 divided by 14,641, which if we change that to a decimal is 1 minus 0.448, which is approximately equal to 0.552, or 55.2% will not be satisfied with the product. The table below shows the camp attendance for 3 age groups of students in one town. Find the probability that a listed student attended camp. So what we want to do first is we want to figure out how many total students attended camp, which is 220, and then the total amount of students that were in the town, which is 478. So the probability of them attending camp is approximately 0.46, which is about 46%. The probability that a child in the 8 through 10 age group from the town did not attend camp. So that's 62 students divided by the total surveyed is approximately 0.13, or about 13% of the students in ages 8 through 10 did not attend camp. You randomly select 2 cards from a standard 52-card deck. Find the probability that the first card is a diamond and the second card is red if you replace the first card before selecting the second. When you replace the card, this is considered to be an independent event because drawing the second card has no bearing on what you drew on the first card because you're putting it back in the deck. So, first card is a diamond. There are 13 diamonds out of 52 cards in the deck, and when I put it back in, I want to draw a red card. There are 26 red out of 52 cards. That's going to be 1/4 times 1/2, which is 1/8. 1/8 is exactly 0.125, which is 12.5%. Now this time we're not going to replace the card. So now we're going to be dealing with a dependent event. So we still multiply together. The first card is a diamond, 13 out of 52. But I'm not going to put that diamond back in the deck, so I'm only going to have 51 cards. The diamond is also a red card. So now, instead of being 26 red cards, since I took a diamond out, there will be only 25 of them. That's going to be 1/4 times 25 over 51. That comes out to be 25 over 204, which is approximately equal to 0.123, or 12.3%. In the next example, 3 children have a choice of 12 summer camps that they can attend. If they each randomly choose which camp to attend, what's the probability that they attended all different camps? Well, that's going to be a dependent event because the children, it depends on the one who chose previously. So the first child has 12 out of 12 camps to choose from. Once one camp has been selected, then the next one has only 11 out of 12 to choose from, and the third has only 10 out of 12 to choose from. So multiplying those together and simplifying, we have 55 out of 72, which is approximately equal to 0.764, or 76.4%. That 3 will pick different camps to go to. In one town, 95% of the students graduated from high school. Suppose a study showed that at age 25, 81% of the high school graduates held full-time jobs, while only 63% of those who did not graduate hold full-time jobs. So what's the probability that a randomly selected student from town will have a full-time job at the age of 25? I think a little diagram could help explain this problem. So there are 95% of the students who graduated and 5% did not graduate. Of those 95%, at age 25, 81% had a job, a full-time job, and 19% did not have a full-time job. Of the 5% who did not graduate, 63% were holding down a full-time job, and that would leave 37% who were not. So when we take a look at it this way, we want to know the probability that a randomly selected student from the town has a full-time job. So we have 95% and 81%. So we take 0.95 of the 81%, and we add that with the 5% who didn't graduate, but 63% of those have a job as well. So we have 0.7695 plus 0.0315, and that equals 0.801, which is approximately 80.1% of the selected students from town have a full-time job at the age of 25. It's important to remember that if the events are independent or dependent. So if they're independent, we simply multiply them together. If they are dependent, we have to determine that probability of A times the probability of B given that A happened. And don't forget the conditional probability. Also remember that if you are replacing or not replacing, if you, for example, are doing drawing of cards, etc.